Welcome to the Demystify Sci podcast. I'm your host, Anastasia.
I'm Michael Shilo.
And today we are talking again with Dr. Avi Loeb. He is staging an expedition to the ocean off of Papua New Guinea to find evidence for a recently sunken extraterrestrial object, and the expedition is slated to begin in summer of 2023. And so we talked to him about the process of getting ready for the expedition, the pushback that he's been getting from the community, the Galileo Project, any kind of updates on the things that he's working on, some stuff about fundamental physics in there as well. And at the very end, we get to AI. So we really cover the entire scope of pretty much everything that there is to talk about in terms of physics.
We also get some interesting pushback on the recent natural explanation for Oumuamua, which Dr. Loeb is convinced is an inadequate explanation. So we get into the details of those two papers that just came out.
If you like the conversation, leave a comment, press, I think that there's like a little thumbs up button somewhere that you can press. Tell a friend, because growing through word of mouth is the absolute best thing we can do, because the algorithm has decided that we are nowhere near polarizing enough, so help us out that way. And if you really, really, really like what we do and you've done all these things and you are casting about for how it is that you can help us, come join our Patreon. You get both episodes that we release every week on Saturdays. You also get access to a weekly patron chat where you get to know more people from the community that are interested in the sorts of questions that you find yourself plagued by. And you help us grow. You help us become better. You help us get more guests. You help us put more money into the show. Ideally, in the long run, we're going to be doing live shows. And so it's not going to be over Zoom with tinny audio. We're actually going to be in the room with people. And ideally, down the road, when this grows to be as big as we need it to be, we're going to start giving grants to people who are studying small things that cannot be done inside of the academy. Because what we really want is we want an ecosystem that is more than what we have right now in the sciences. We want cutting-edge ideas to be able to get their fair play. And the only way to do that is by putting your money where your mouth is. And so that's the long-running goal here. So you can help us get there by supporting us on patreon.com/demystifysci.
Sit back, relax, and we'll see you guys next week.
The scientific revolution starts now.
The Demystify Sci podcast.
Let us see in the dark.
So we are planning to have the journey, the expedition, in the summer. We are developing now the machinery necessary to retrieve any fragments left over from the first interstellar meteor. And what was special about it is it exploded relatively low in the atmosphere, about 10 kilometers above the ocean's surface. So given that it was moving extremely fast, since it came from outside the solar system, we figured that it was tougher, at least by a factor of 10, than all other meteors that were previously discovered from the solar system. And that makes it a puzzle. Was it created by a natural process, by a system very different from the solar system? Or perhaps it's artificial in origin, made of some alloy that was manufactured by a technological civilization. So the way to find out is to retrieve fragments and check their composition. And that's what we hope to do. And for that, if the fragments are magnetized, we will use a magnetic sled to collect them from the muck on the ocean floor. And if they're not magnetic, we also have a sluicing device that we might use. So that takes some effort for us to manufacture these two pieces of equipment. And then we'll have a mass spectrometer that will try to identify the composition of the fragments on the boat, but we will do a much more careful job in the laboratory afterwards if we bring anything back. So that is the main challenge, bringing something back. And of course, it's very challenging because the ocean is deep, about a mile deep down there, and fragments are distributed over a large region. And the key to the success of this expedition was to localize the site to within a kilometer squared. And we were able to do that very recently, over the past month, with my student Amir Siraj. based on data obtained by a seismometer on Manus Island in Papua New Guinea. So that allowed us to pinpoint the distance of the meteor explosion very precisely, and that's where we will go.
How will you be able to sort out this material from, say, other meteorite junk or other space debris?
That's an excellent question, and the idea is to look at other regions that are remote and compare what we find there to what we find in the meteor site. So only things that appear unusual will be regarded as perhaps belonging to that meteor. And also, this meteor was roughly 0.5 meter in size, like a big watermelon. And when it exploded, it released a few percent of the energy output of the Hiroshima atomic bomb. So everything in it was melted, given the huge amount of energy released as a result of the friction with the air. And therefore, what we expect to find are spheroids. These are small spherical particles that were melted and rained down like hot rain. And then as they met the ocean, they, of course, raised some steam, but eventually ended on the ocean floor. And so they should look different than what you find from other sources, which have nothing to do with such an explosion.
What's the ocean bottom look like there? Have you guys done recon?
It's supposed to be just mud, the muck, very sort of sluggish thing. But we can't send a human down there. It's so deep. And so we developed the machinery necessary for us to do it remotely from the ocean surface.
Yeah, because I want to know more about that process. So you are a scientist who has studied, astrophysics and comets, and now you're going and you're mounting this ocean expedition. What is the arc by which you go from working with telescopes to working with, magnetic sleds and sluicing machinery?
Well, that's an excellent question. The good thing about studying physics from basic principles is that it applies everywhere, irrespective of what you're looking at. So that's what the advice I gave to 3 students that are prospective PhD students at the Harvard Astronomy Department. They came to my office for career advice, and I said that Pablo Picasso, when he started his career, he learned how to paint very realistically in the traditional way before he later invented his cubism, which was a breakthrough in the way that paintings were done. And so I told these young students, fledgling scientists, that they should start by studying fundamental principles, because that would serve them in anything they do later. And only late in their career, they should attempt to break new boundaries or try to innovate in a way that is disruptive, the way that Picasso did late in his life. So since I started this way, that's why I gave them this advice. It serves me very well, because I can basically understand almost any context in which there is scientific interest. And in particular, this expedition, deals with some very known physics involved. And of course, I read the literature on meteors and meteorites and fragments that may be left behind and so forth. But we might be dealing with a completely different object, because previously all space rocks were from the solar system, and therefore they were made at most, in terms of their composition or material strength, they were made from the toughest material that was ever used was iron. So we don't know if this object was made of iron or maybe some stainless steel or some other. And so what we find may depend on what this object was made of, and that could be quite different from past experience. And only 1 in 1,000 rocks from the sky originates from interstellar space based on the statistics. So, it should be quite unusual, and we hope to find it.
you have this wider hypothesis that you advance in one of the papers that we'll pin down below, where you analyze the idea that potentially this material could have originated from a particular extraterrestrial structure, these Dyson spheres, which I didn't realize were advanced in the Olaf Stapledon piece, because that was a really influential book on me when I was younger. But can you get any clues about can you make a prediction about the material composition of this object based on the technological requirements of a Dyson sphere, if it were to be the case?
Well, first, if it's very difficult for us, given what we know about material strength, to imagine engineering a Dyson sphere as a rigid sphere, because it is subjected to very strong shear and stress and buckling forces, and so we cannot really do it with present-day materials. But a way around it would be to make it out of tiles that are basically solar sails. These are very thin membranes that are pushed out by the radiation from the sun, the sunlight, and you can arrange them to have just the right thickness so that the gravitational force pulling them towards the sun is equal to the radiation force trying to push them out, and then they will hover above the sun. And so if you make many of those tiles, you can basically surround the sun with a structure that could harvest the energy output from the sun, and the same can be done for other stars. What I argued in my paper was that while our civilization might use such a structure for a while, eventually the sun will change its properties. It evolves, it becomes brighter, and it could push those tiles out. And also there could be damage caused by asteroids puncturing this structure, and if we don't maintain it, it will be destroyed. And as a result, there would be pieces of Dyson spheres flying into interstellar space, much more likely than asteroids, because asteroids are gravitationally bound to the star, and in order to kick them out, you need to provide them with a very large boost in their speed. You need to kick them. Whereas if you have a tile that is a solar sail, a light sail, it's very marginally bound to the star. In fact, it's almost not bound at all. And so a small kick could lift it out. And actually, if the star warms up, brightens up, it will be naturally ejected. And that would make for a large population of interstellar objects that are just the pieces from broken Dyson spheres. And I suggested perhaps Oumuamua, this first interstellar object discovered by a telescope in Hawaii, perhaps that was such a piece because it appeared to be affected by sunlight. That was my interpretation of its excess acceleration that was non-gravitational. And it could be such a piece. And the same is true for those meteors, two of them that we discovered with my student Amir Siraj, and they exhibited very high material strength. So the question is, why were they made from a material that is so tough? And perhaps because they were part of a Dyson sphere.
I have a pretty basic physics question about the light sails. So a photon is not in conventional physics seen to be a material object, and yet it has this momentum that it can transfer to an object. How do you square that in terms of fundamental physics?
Well, it's really simple because if you imagine a bullet bouncing off a wall, it gives the wall a kick, or a racket hit by a tennis ball is bouncing back. Any tennis player knows that, right? So we know that material objects that move at slow speeds do give a kick to whatever they collide with and bounce off. But if you try to compare their energy to their momentum, the momentum is the amount of kick that they give. It turns out that the momentum is the energy times 2, a factor of 2, divided by the speed of the object, because the kinetic energy is 1/2 times the momentum squared over the mass, or 1/2 the momentum times the speed. So the momentum is the energy over 1/2 of the speed. And if you imagine taking the speed to be the speed of light, then obviously the momentum you give a surface would be much smaller, because you take the energy and divide now by the speed of light, which is far greater than the speed of a tennis ball. Okay, even if you remember this mission DART that NASA sent to collide with the moon of an asteroid, that spacecraft moved at a speed that is 10,000 times slower than the speed of light. So it gave it a kick, but if it were moving at the speed of light, for the same energy that you invest in the spacecraft, it would give it a much smaller kick, 10,000 times smaller, just because the momentum is the energy divided by the speed. Okay, so a photon is a particle moving at the speed of light, and so it gives very little momentum for a given amount of energy that is invested in it. But the advantage of a photon is that if you have a sail that you want to bring close to the speed of light, that is the kind of tennis ball that you want to use that moves already at the speed of the terminal speed of the sail, right? So you don't want to take something much slower because it will never catch up with the sail. So for the purpose of getting to high speeds, light sail is ideal. Also, if you don't want to invest any energy in propelling an object and you just want to use sunlight, you would make it thin enough such that the sunlight would push it out. And I actually wrote a paper talking about kites that are pushed by light from stars, and you can imagine them hovering above the Milky Way just because starlight is keeping them high up compared to the gravity that tries to bring them down. And it's just like a kite flying in the wind, because a sail on a sailboat, which is pushed by the wind, is just like a light sail, which is pushed by photons. The only difference is that the molecules of air that are pushing a sailboat move at a speed that is actually 100,000 or actually 1,000,000 times smaller than the speed of light. So they are much more effective. You don't need as much energy for them to push the sail. But the same mechanism works in a light sail.
Yeah, technologically, it seems feasible. It seems like it would really strengthen the hypothesis if we could find some potential Dyson spheres out there when we, turn our telescopes towards the stars. What would we be looking for? How would we find one of these dark stars? Would it be glowing like a black body? Would it look like a brown dwarf? Would it look like a black hole? What are we looking for?
Yeah, so the idea is that you imagine placing the Dyson sphere at a distance, let's say, of the Earth from the sun, and then the energy coming from the star will be absorbed by it. And as a result, this object will be warmed up, heated, and will radiate on its own, but at a much lower temperature, because now the surface area is so much greater than the surface of the sun. And as a result, the temperature for it to emit when it balances the heat input by radiating it out, the temperature would have to be much smaller. So if the distance of the Earth from the sun is a factor of 100 times the size of the radius of the sun, which is the case, then the temperature will be a factor of 10 actually times smaller, because the area goes like radius squared, and the black body emission goes like temperature to the 4th power. So altogether, we're talking, the Earth has a temperature of around 300 degrees above absolute zero. So this Dyson sphere will have a temperature of around that much at that distance, and that translates to emission in the infrared, because the soldiers at night, our body has roughly the same temperature as the Earth, right? And so when you put these goggles, infrared goggles, you see people walking at night, and so you're talking about infrared wavelengths. And so the suggestion was made already originally by Dyson, but later on by other people, to look for infrared emission from stars that are otherwise much hotter. And unfortunately, such observations are confused by dust surrounding stars because it's the same mechanism. And so we see a lot of stars enshrouded in dust, have nothing to do with the Dyson sphere. We can tell that from the properties of dust showing up in the observed radiation. So people have searched for Dyson spheres and didn't find any example of a candidate for an artificial megastructure. We don't know whether they exist, but of course, only a small fraction of the stars in the Milky Way were monitored. And moreover, one thing to keep in mind is most of the sun-like stars were formed billions of years before the sun, and the sun within about 1 billion years will make the Earth inhabitable. So we will have to migrate somewhere else, and that means that most of the stars already did that to a planet that could have given birth to a technological civilization like ours. So most of the civilization that predated us are probably either migrated somewhere else or dead by now, and their Dyson spheres probably washed away, as I mentioned before, or broken. And so it's hard to tell how many of them are still around, And obviously we don't see radio signals coming from surveys of many stars, millions of stars that were done by now. So it may be a small minority of stars that have Dyson spheres that are operational, let's say, right now. People have also looked for an extension of Dyson spheres that correspond to the energy of a whole galaxy being harvested, but that obviously was not seen either.
Yeah, because it seems to me like it would be basically a supermassive brown dwarf, something that had way too much mass for how much luminosity and temperature was available for it.
Yeah, well, also bigger in size, because if you want to put it, let's say, at the Earth-Sun separation, that could be in principle resolved by modern telescopes.
Another thing that comes to mind, we just spoke with the Princeton astrophysicist Eric Sternstein, who studies the heliosphere, and it seems like what they're learning about the heliosphere, it's a hard one to say, what they're learning about the heliosphere is that it stabilizes the solar system, in that there actually is this, bow shock at the edge, which protects us from cosmic rays and interstellar chaos in general. And it seems like if you closed off the sun, you might disturb that process somehow. And
yes, you would.
Maybe in an effort to get around that, you would vent it somehow. So you would see perhaps some anisotropic venting or jets or something like that as well.
Yeah, that's a very good idea. Or you can put the Dyson sphere outside the orbit of the habitable planet on which the civilization resides, and then extract the energy from it. This will also allow the civilization to benefit from the star interior to the Dyson sphere. So it will still be illuminated.
Still get your rays at the beach.
Yeah, the other thing to keep in mind is the solar system extends way out beyond the heliosphere. So the heliosphere goes out to 100 times the Earth-Sun separation. That's where the solar wind, the particles coming off the sun, are stopped by the interstellar medium. And the solar system extends 1,000 times farther. It extends to about 100,000 times the Earth-Sun separation. And that the outskirts are the so-called Oort cloud of all the Lego pieces, the building blocks that were used in the construction project of the planets. And one thing to keep in mind is those icy rocks in the Oort cloud are exposed to the same cosmic rays and the same interstellar medium that interstellar objects are exposed to on their journey towards the solar system. So some people suggested just recently, a week ago, that maybe Oumuamua was a regular comet, a water iceberg, and it exhibited its unusual properties, for example, of being pushed away from the sun without showing a cometary tail, because it was exposed to interstellar cosmic rays more than regular comets. Well, that's not true, because the long period comets that we see originate from a region that is not protected from the interstellar cosmic rays. So we see them as comets, and if you open any dictionary, you will immediately see that comets are defined to have a coma, surrounding gas and dust that was evaporated from their surface. And if they don't show it, they are not comets. And so inventing the concept of a dark comet when we see icy objects that are exposed to the same interstellar environment is just, it doesn't describe what we know about comets versus asteroids. And it's sort of like going to the zoo and looking at an elephant and arguing that it's a zebra that doesn't show its stripes. We know that an elephant is a completely different animal, and the same was true about Oumuamua. And this paper that appeared in Nature last week, claiming that perhaps it was a water iceberg that was in which some of the molecules of water were dissociated by cosmic rays, breaking them into hydrogen and oxygen. That model is not viable because they assumed a certain temperature on the surface of the iceberg when it's warmed up by sunlight, and they took the heat input from sunlight and balanced it by the heat output by radiation from the surface of the iceberg. That gave them a temperature of about 100, 150 degrees at the location where Oumuamua was observed. The mistake they made was not to include the energy loss from the energy needed to dislodge those hydrogen atoms from the lattice. And when we included that in a paper that we posted a day after this Nature paper appeared, we showed that the temperature is reduced by a factor of 9, making the model untenable, because at that low temperature of about 20 degrees above absolute zero, the hydrogen will not move out at a high enough speed to propel the object the way it was seen. So Oumuamua would not be propelled by the rocket effect. And so the idea that it was a water iceberg is just not tenable.
So, but this seems to connect, in my mind, to the tendency to include dark material or dark factors when things don't make sense in astrophysics.
That's right. That's exactly right, because we've seen this movie before when most of the matter in the universe was inferred to be dark matter. We don't know what it is. It was first discovered about 90 years ago by Fritz Zwicky, when he realized that the clusters of galaxies have more mass than you can account for in the form of visible stars and galaxies. And those galaxies were moving too fast to be bound by the visible material. And so he called it invisible matter. And since then, we called it dark matter. But this is just to label our ignorance, and we still don't know what it is. In fact, since I started astrophysics about 35 years ago, the most popular explanation for the dark matter was that it's a particle associated with a new symmetry of matter called supersymmetry. And then people said, okay, well, we can actually forecast the properties of this symmetry, and we could build an accelerator that will smash particles, protons, and produce these lightest supersymmetric particles that account for the dark matter. And this experiment was funded at $10 billion. It's called the Large Hadron Collider. We haven't found the dark matter. And we know that the matter in the solar system is not dark matter because we see it. And so most of the matter in the universe is not represented by the solar system. Now, there are two morals to this story. First, when we are detecting the first 4 interstellar objects over the past decade, 3 of them appear to be very different from solar system rocks. Nevertheless, my colleagues tried to argue, most recently a week ago in Nature, that these are still very familiar objects. It's sort of like me being the kid in Hans Christian Andersen's tale, who argues that the emperor has no clothes because I look at this object Oumuamua and I say it has no clothes, no cometary tail. The emperor is Oumuamua. Whereas the other people watching the parade argue, no, the emperor has beautiful clothes. They are just invisible. And the strange thing is these are younger colleagues, and I would argue younger people should be excited about new objects that do not match what we know from the past. They should say, well, that's an opportunity to learn something new. Maybe the objects coming into the solar system from outside are not the same as the objects we find in the solar system. Just like you go out to your backyard and most of the time you see the same rocks that you saw for many years in your backyard. But every now and then you might see a tennis ball that was thrown by a neighbor that came from the cosmic street, in our case of the solar system. And you should be open-minded to assuming that it's not a rock. And so that's one lesson to be learned. But of course, the second one is that what lies outside the solar system is not what we find in the solar system. Just the same way that what lies in our street is not the same as what we find in our backyard.
There seems to be a pretty common tendency to not be able to really fold that into an established field, though. And I don't know if you saw, there was a paper, I think it was probably a month or two ago at this point, that was talking about the decrease in disruptive science papers and technologies.
Yes, I was very disturbed by that paper, yeah.
And so there's some decent criticisms of it, which one of the criticisms was the way that they parameterized their model. Because from what I understand it, they did their analysis on the basis of looking at citations, where they took disruptive papers to be those that didn't cite previous work in their field as the prerequisite for the argument that they were making, where the idea is that a disruptive paper is one that cannot, by definition, cite other landmark works. And so you can make the argument that their analysis was limited because if the social mores of publishing have changed so significantly that you cannot publish even a disruptive work unless you cite other work and kind of like hide what it is that you're doing, that the analysis misses that.
That's a very good interpretation, actually. And I can give you, I mean, this is not the field study, but I can give you two examples that represent the situation in my field. So, for example, I attended a PhD exam of a student at the Harvard Physics Department. And the thesis was to develop a model that would test the paradigm of cold dark matter, which is the most popular in cosmology, based on the clustering of galaxies. Okay, so the model proposed a test comparing what the model predicts for cold dark matter. And I asked the student, I said, okay, well, now let's imagine that future data will show results that deviate from your model. What would you conclude? That would you rule out the cold dark matter paradigm if that happens to be the case? And the student said, no, I will just realize that I didn't include all the important ingredients in my model. Okay, so that shows you the atmosphere in academic culture, in the sense that the student does not feel secure enough to deviate from the beaten path. Now, you might say, okay, maybe it's a student, maybe the tenured professors behave differently. Well, no, I would argue that it's even worse among tenured professors, even though they have job security. I'll give you an example. We had a colloquium by a senior faculty member who described what is called the swampland landscape of string theory. Okay, so that's a model developed based on what we know on string theory, which is completely hypothetical. We haven't tested string theory yet experimentally. So at the end of that colloquium, I asked the speaker, I said, so let's imagine that data from the cosmic microwave background in the future will deviate from the forecast that you presented based on the swampland landscape model of string theory. Will that rule out string theory? And this senior professor said, no, it will just rule out the conjecture that I used in establishing this model. String theory must be right. And let me remind you, string theory was never tested before. It's just a mathematical construct that for 50 years was worked on by the mainstream of theoretical particle physics. And so you ask yourself, if the practitioners are not willing to entertain the possibility that the idea they worked on is incorrect, how would we ever test it? And moreover, there is no, in the foreseeable future, there is no proposed experiment. And moreover, there are versions of the mathematical construct that are so different from each other that we don't know which one to pick. And so what I'm asking is, how come this practice became so fashionable? Because it violates the tradition of physics, of testing ideas through experiments. Albert Einstein, between 1935 and 1940, made 3 mistakes. He said that gravitational waves do not exist. He argued that black holes do not exist. And he argued against quantum mechanics have spooky action at a distance. And actually, all 3 of them were verified experimentally, and Nobel Prizes were awarded for people who verified those ideas over the past 5 years. So 3 independent groups of people that verify that black holes exist, verify that quantum mechanics does have spooky action at a distance, and verify that gravitational waves exist because they were detected by a laboratory experiment, they got the Nobel Prize in the last 5 years. Now, what does it show you? It shows that when you work at the frontiers, even if you are Albert Einstein, you could make mistakes. It's not obvious what's true and what's not. But it also shows you that we should be modest and learn from experience, from experiments, rather than assume that we know the answer based on theoretical reasoning. We already made that mistake when people argue that we are at the center of the universe since the days of Aristotle. And then when Galileo Galilei tried to argue otherwise, he was put in house arrest. That was not popular, but the Earth continued to move around the sun. And therefore, nature is very often more imaginative than we are. And we should be modest to accept the guillotine of experiments. If you don't put your head under the guillotine, you would never know if the theory that you proposed is correct or not. And you may spend your entire life doing mathematical gymnastics on an idea that is not worth much. And I would argue, it's just like having a plumber that defines himself as a plumber come to your home and then saying, I don't think I can fix your toilet. I cannot fix your plumbing issues. I just prefer to imagine myself as an actor in the metaverse, and he puts goggles on his head and he lives in a different world. And you say to yourself, well, that's not a plumber. You can't argue that you are fulfilling the duties of the profession if you're not performing according to the narrative of the profession. And in the context of physics, we are supposed to describe reality. I mean, you can do mathematics and be called mathematician. That's perfectly fine. But if you want to call yourself a physicist, you have to propose experimental tests of your ideas within your lifetime.
It seems to me like a huge part of the problem with the dark stuff, the dark matter and all of that, is that these anomalous effects of cohesion, like the rotation of the galaxy, they're reified into actors, right? The dark matter is really a problem with the way that we understand the dynamics of systems that are in motion, but we turn them into an actor like it is a thing itself, and then all of a sudden it's at the center of the discussion as opposed to being the place where we can come up with a material solution might be. Like, I wanted to run one thing by you. We played with Eric Sternstein with this idea a little bit, but like you mentioned earlier, the Oort cloud extends almost halfway to the next solar system. And presumably those solar systems also have Oort clouds that extend. And presumably there's like some sort of interactions going on. Presumably there's the potential for some sort of cohesion that goes beyond gravity, because it seems like gravity, like dark matter comes out of the necessity for gravity to explain everything in these dynamics. But if there's some other actor, if these things are bound to one another in ways that we don't yet understand, maybe there's a material basis for that, where we're looking in the wrong tunnel for the answer.
Well, you are right that it's possible if each star has an Oort cloud, and indeed those are touching each other, just like billiard balls that are densely packed. And there is a lot of exchange of materials, but they are not rigid objects. They are very rarefied, because the distances between the rocks are far greater than their size. So most of it is empty space, and Oort clouds can pass through each other without a problem. But it's true that many of the objects that may exist in the Oort cloud may have been borrowed from neighboring stars. And especially if the sun was born in a cluster of stars. And so there might be a lot of interstellar material trapped in the Oort cloud. And, it's just like families living in a commune. Sometimes you don't know who are the parents,
It took me a second to process. That's quite the analogy.
But in the context of dark matter, that's a more serious issue, because there are two possibilities. Either there is another substance, matter, that is not interacting with light, and that's the origin of the idea of dark matter. We just don't know what this matter is. It could be primordial black holes, for example. Then you would never see them, because they are tiny and they exert only gravitational force. They don't interact with anything we know. The second possibility is that gravity is modified, and that is not at all being followed. This idea is pursued by a very small fringe of the academic community, and to me, it's not at all clear.
Is this the MOND?
MOND, exactly. And it was suggested 40 years ago, and the data on the dynamics of stars in galaxies is very well fit by this theory. It's quite remarkable 40 years later that there is no clear deviation from the predictions of this theory in galaxies. But the one deficiency of this model, MOND, is that there is no extension of it that applies to the universe at large, that appears to be consistent with all the data we have on the universe. For example, the cosmic microwave background fluctuations, or the clustering of galaxies on large scales. Whereas the dark matter hypothesis is able to unify the large and the small. It's quite possible that we simply don't have the right ideas about how to generalize MOND from the scale of galaxies to the scale of the universe. It's quite possible, because to me it's still quite remarkable that it works on galaxy scales. And of course I was familiar with MOND since I worked in astrophysics for 35 years. 5 years after MOND was invented, I entered astrophysics, and I knew the person who invented it, and Mordechai Milgrom, and followed it over the years. And I still regard it as an amazing success story in the context of galaxies, but not in a larger context. One way to test MOND that I thought about just this year, and when I mentioned it to Milgrom, he never thought about it, is the following. Basically, what MOND says is that when an object is accelerated at a very low acceleration, it responds to forces much more strongly. So actually, it's the acceleration squared that is proportional to the force at low accelerations, rather than the acceleration being proportional to the force as Newton imagined. That's why it's modified Newtonian dynamics. And what I argued is, if you imagine a rocket, in the context of Newton, a rocket needs to carry a huge amount of fuel in order to accelerate to a speed that is beyond the exhaust speed of the gas that is being shot out from the back of the rocket. So that's why it basically, the amount of mass that it needs to carry grows exponentially with the terminal speed of the rocket. So that's why you see these rockets with a huge fuel reservoir. And all of the spacecraft that we ever launched to space never exceeded 1 part in 10,000 of the speed of light. So they can't go beyond that because the amount of fuel that you need to attach to them to start with is exponentially larger if you just want to get a small increment in their terminal speed. So in the context of MOND, that's not the case. In fact, you can imagine a rocket that carries in fuel as much mass as it has in its payload, not exponentially large. But then the fuel is burnt very slowly, and it pushes the rocket with a very small acceleration below the threshold of MOND. And if it does it for a very long time, let's say 1 billion years or billions of years, then the rocket can even reach the speed of light. If it does it for long enough time at a small acceleration, simply because you get much more than you pay for, in a way, because the acceleration squared is proportional to the force. And the force is simply the momentum given by pushing material out of the rocket that is pushing it forward. So it turns out that in the context of MOND, you can get to very high speeds with very little fuel. You just need to be patient because it takes a long time.
That's a multi-generational experiment there.
And Milgram didn't think about it. I just thought about it by one of these pandemic days that nobody was knocking on my door, so I could think about it.
I guess that what I'm curious about is if anyone is considering non-gravitational cohesion mechanisms by which stars could stick to one another, is there any kind of stickiness that anyone is,
No, that's not okay. We know from cosmology that, I mean, if you forget about MOND and modified gravity, if you just imagine standard gravity, we know that the amount of ordinary matter that was in the early universe when hydrogen, so remember, in the first 3 minutes of the universe, the temperature was so high and the density was so high that hydrogen protons basically fused to make helium. And that is the origin of the helium we see in the sun. Most of it was made in the Big Bang. And in any star, about a quarter of the mass was made in the hot and dense 3 minutes after the Big Bang. Okay? So we can infer the amount of ordinary matter that existed in the universe per unit volume, and then compare it to how much dark matter you need to explain the motion in galaxies or the cosmological expansion. And you find that there is just not enough in ordinary matter based on the abundance of helium relative to hydrogen.
So this is based on like expansion dynamics, essentially?
Yeah. So if you use Einstein's theory of gravity, you can figure out, you can go back in time. The universe was hotter and denser because we measure the temperature today of the cosmic microwave background, so we know what the temperature was as the universe, as you go back in time. And you can calculate how much helium would be produced in the first 3 minutes after the Big Bang, and you find that it matches what we see if the amount of ordinary matter is about a factor of 6 smaller than the amount of dark matter.
Well, it also depends on the interpretation of the CMB being correct, right?
Right. No, so all of that is in the framework of Einstein's gravity. So then there is no doubt as to how you should extrapolate back in time. Of course, if gravity is modified, you have to worry about how to extrapolate back in time, and then you may avoid this constraint that I was mentioning.
I mean, something that was really... So we were talking a while ago to John Moffat from the Perimeter Institute, and he has this variable speed of light theory, and we were really trying to dig into the new James Webb data, because it was just after the really high redshifts were coming out, and we were kind of picking on him a little bit, and we were asking if anyone was studying different explanations for redshift. And we came up against the fact that there is a really stiff wall where he was like, no, we don't study that. This is a given. It's almost a philosophical question of other possible explanations because it's so far outside the realm of what is considered possible or probable or likely that there's no one sitting around. You know, there's like Helton Arp who's like, hey, I have an atlas of anomalous galaxies. I think that stuff is weird. And then you run across people that are kind of on the fringe that are like, hey, something's weird. But it's really strange to me that at the heart of the academy, the place where there should be a plurality of theories, even about these really, really fundamental things, it seems like there's just one voice that has agreed that we don't work on that. That's
No, so
fixed.
the alternative to along the lines that you're suggesting, based on known physics, would be for the source of light to move away from us at a high enough speed, close to the speed of light. Then you would get redshift, and you are correct that if what we're seeing are sources of light that were, for example, shut out of a black hole, let's say, at a very high speed, close to the speed of light, away from us, they would look redshifted. It has nothing to do with a cosmological redshift. It's just because of the Doppler effect. Okay? Now, you may ask, why wouldn't we consider those galaxies as fast-moving blobs of gas? The answer is, well, at least the sketchy data that exists as of now implies that you can describe the spectrum that they emit based on the spectrum of galaxies. So it seems consistent with that. Now, I should say, first, let's talk about the puzzle. The puzzle is that those early galaxies, and by the way, this is a field of study that I pioneered some 30 years ago. There were only a few people interested in the first galaxies, the first stars, and that was my first study, the first research frontier that I sort of initiated, and I wrote 2 books about it. One of them was published in 2012, and the other in 2010. The one in 2012 was in anticipation of the Webb telescope to make predictions that could be tested. And I always said that if the Webb telescope gives us data that violates the forecast in my textbook, I would be even more happy than if it confirmed it, because we will learn something new. Now, what do we learn from the latest data from the Webb telescope? That galaxies above redshift 10 appear to produce much more ultraviolet light than we would have anticipated. And so that makes them interesting, because it means that somehow they have sources of UV light that are different from what we expected. And one possibility is that the first stars were much more luminous in UV. They were more massive. And in fact, that was a prediction, theoretical prediction, that the first population of stars was more massive. It's called population 3. What is surprising is that you see evidence for that in galaxies above redshift 10. And in fact, I'm in the process of writing a paper that explains it, because in one of my earlier papers from 20 years ago, we actually predicted how the fraction of light produced by the first generation of stars would vary in high redshift galaxies, and it perfectly matches the observations from the Webb telescope. It's just that nobody made that point, so we are writing a new paper now about it. But I would say this is a mild surprise. This is not a major fundamental surprise. Finding galaxies to be more luminous than expected, basically saying that there might be a larger population than we expected of massive stars that produce a lot of UV light. They are excellent factories of UV photons, and that's all we are seeing. So far, there is nothing really fundamentally surprising in the Webb data.
Do you think that we have a really, really, really solid understanding of what light is?
Well, with respect to light, I would argue probably yes, because it's electromagnetism, and it's being used everywhere. It's easy to detect, and we are using it for all kinds of gadgets. It's being tested, and it's tested to an exquisite precision. Like the fine structure constant is known to I don't know how many decimal points, and moreover, it appears to describe what we see from early cosmic times extremely well. So I would argue electromagnetism was tested so much simply because the interaction is strong that there is very little room for deviation from what we know about light, about electromagnetic interactions and so forth. But for gravity, that's not the case, because gravity is very weak, and there could be surprises on cosmic scales. And one of them is, of course, the dark matter. We talked about it. The second one is what is called dark energy, which is basically the cosmological constant Einstein imagined a century ago. And it produces repulsive gravity. And the way to understand it is because it has negative pressure. So it turns out that in Einstein's gravity, pressure gravitates. And when you add the effect of pressure to the effect of the mass density of the vacuum, it turns out to produce negative repulsive gravity. So just imagine Isaac Newton sitting under a tree. Instead of an apple falling over his head, if gravity was dominated by the vacuum instead of the Earth, then the apple will fly away from Newton at an accelerated speed and will fly out to space, to outer space. And that's what we see galaxies doing relative to us. They are flying away from us at an ever increasing speed, and the universe is accelerating. The Nobel Prize was awarded. 2 out of the 3 recipients were graduate students in the astronomy department at Harvard when I arrived. So I'm familiar with their story. And in fact, one of them told me that the reason he did this research is because he studied cosmology in my class. And in my class, I said, here is a way for inferring whether the universe accelerates or decelerates based on distances to sources of light. And he was struck by that, and he claims that motivated him to go in that direction. So at least, students pay attention to what I say. I wouldn't say the same about more senior people. So anyway, there is this dark energy. We don't know what it is. And I'm now working on an interesting paper that talks about, imagine that we understood what it is so that we can engineer the dark energy and, make an object made of it, that is made of it. And this object will have a negative mass. Okay, it will repel gravitationally anything around it. So if you think about it, imagine putting such an object that, let's say, has exactly the mass of the Earth next to the Earth. Okay, so the Earth is made of a positive mass, the mass of the Earth. It produces attractive gravity. That's why we are stuck on the surface of Earth. In order to, it's like a prison. For us to escape from it, we need to exceed the escape speed from the Earth. Otherwise, we're stuck on the surface. That's positive, attractive gravity. But now put a negative mass next to it with the same mass. So the Earth would pull it, but this negative mass will push the Earth away from it. So what will happen is that the Earth would be pushed away and will pull this negative mass along with it. And this pair of masses, one positive, one negative, will keep accelerating indefinitely up to the speed of light. So, and the acceleration would be roughly the same as you feel on the surface of Earth, 1g. So it will be very comfortable. You will have propulsion at 1g with no fuel, just a negative mass next to a positive mass. And if you keep accelerating at 1g for 1 year, you get close to the speed of light. If you take 1g times 1 year, that is the speed of light by coincidence. And if you keep doing that, accelerate at 1g, this very comfortable acceleration that we feel right now on the surface of Earth, if you keep doing it for several decades, you would get so close to the speed of light that during a human lifetime, you can traverse the entire universe, billions of light years. Why? Because the journey will take less than a few decades in your frame of reference. Time dilation would make it very short for you, while the rest of the universe is evolving for billions of years. So if we could engineer such a device, then we could travel across the entire universe in our lifetime. And the question is whether another civilization that, let's say, is much more advanced than we are and may have harvested the dark energy and engineered it, maybe they produce such objects. Now, such objects would move at the speed of light when they cross large distances, and we would never notice them. Astronomers would never notice them because they move so fast that at best they would appear in one image of a telescope, but you wouldn't be able to track them.
We were actually going to have this researcher, Beatrice Villarroel, from the Vasco survey. And the Vasco survey did this really interesting whole sky survey, and they found that over the course of, help me out with this, like a couple of
50
decades.
years, I think.
Do you want to tell it?
I don't know. I haven't looked at the paper in a while, but they essentially just look at stars that blinked out of existence, essentially.
Right. Actually, I met Beatrice just a couple of weeks ago in person.
Oh, cool.
Switzerland. I know her very well. She was a member of the Galileo Project for a while, and and the work is very interesting. It's based on archival data. Now, the only problem with archival data is that we cannot repeat the experiment because whatever is seen happened a long time ago, and moreover, perhaps what was used for detection back then had malfunctioned. It's difficult to rule out these possibilities because you don't have the instrumentation in front of you so that you can verify that the detection was real. And of course, the same applies to unidentified objects that the US government reported about. And in fact, most recently, there were 2 reports from the Director of National Intelligence to Congress. And that motivated me to establish the Galileo Project. There were a few wealthy individuals that came to the porch of my home after they were inspired by my book, Extraterrestrial. And they decided to give me a few $1 million. And actually, the expedition that we mentioned before is funded separately at $1.5 million, again, from private donations. So the spirit behind the Galileo Project is, instead of relying or waiting for the government to declassify data, or instead of looking at past data that was obtained by instruments that were not of the quality that we have now, let's just look at the sky. The sky is not classified. And in fact, the Galileo Project over the past year and a half assembled a functioning observatory. We just had a meeting of the Galileo team a few hours ago in which we were looking at images of the sky because we have infrared, optical, radio, and audio recording of the sky 24/7 from an observatory on Harvard University property.
And so give us an update on that, because we spoke to Massimo Teodorani maybe like a month ago. And so he was still at the point where the first images hadn't yet been collected and analyzed. Yeah,
he's an affiliate of the Galileo Project, but not only that we obtain images, we're obtaining movies of the sky steadily now. And the latest data that I looked at, we can identify objects like an airplane, a bird moving. We didn't see yet any unidentified crazy looking object. But the goal is to have artificial intelligence software that will classify objects and learn from experience. And there are 2 broad classes. One is natural objects like a bird or a bug or a cloud, thunderstorm. Or the second class is human-made objects like the balloons that were shot down by the US government not long ago, drones, airplanes rocket. In fact, I should say that I'm very pleased that the US government shut down some balloons because it reduces the noise for our experiment. I have no interest whatsoever in an object made in China. That's very boring for me. It's of great interest to the US intelligence agencies because they protect the nation, they protect national security. So we are complementary in terms of our interests as scientists. And for us, even one object that was manufactured extraterrestrially is of great interest. For them, they have to figure out what most of the objects are. And so, if we have data that indicates objects of interest to them, I'm happy to transfer it without even looking at it. And if we see natural objects like a bird of some rare origin, I'll be glad to provide it to zoologists. But because both are very boring as far as I'm concerned, I want to see if there is anything else. And in November 2021, I was in the Washington National Cathedral in a public forum, attended by Avril Haines and Jeff Bezos. And Avril, who is the director of national intelligence, she received her bachelor's degree in physics. So I approached her and said, what do you think these objects that you're talking about are? And she said, I don't know. And I believe her. And of course, some of these objects are probably balloons, maybe half of them. But she did not rule out the possibility of an extraterrestrial origin, even when she spoke publicly. Now, I don't believe in science fiction. When Jeff Bezos said he was inspired to establish Blue Origins after watching Star Trek as a kid, I said to Avril, I was never impressed by Star Trek because it violates the laws of physics, and I have a problem enjoying science fiction for that reason. And she said, Avi, we have to work on you.
I feel like Shilo has the same problem. We always watch movies that have time travel in them, and he's like, this doesn't make any sense. I can't watch this.
Well, one possibility to explain these unidentified objects is to argue for time travel, because you would say, okay, well, maybe it represents our future. So, someone from our future is coming to visit us. That's a possibility. However, Stephen Hawking in a paper argued for what he called the time travel protection conjecture. Basically, that there are no closed time-like curves that allow a visitor from the future to come here. And he argued for the laws of physics to forbid that, because it raises all kinds of logical inconsistencies. And we don't know if time travel is possible, and based on what we know, it's not. We don't have any evidence for that. But of course, if we meet someone from our technological future, we might. Now, even if there is no time travel, we might find gadgets that represent our future, because, as I mentioned before, most stars form billions of years before the sun. So if a technological civilization evolved around them, it might have done so billions of years ago before us. And what we would see, the products that we would see from it, may represent our future. And actually, in my latest essay submitted in Medium, every few days I put a Medium essay that was submitted just a few minutes before I joined you. I talk about the fact that artificial intelligence, AI systems, are presenting a very uncertain future for us, because as of now, GPT-4 has 6 times fewer connections in it. It has about 100 trillion connections. That's 6 times less than the number of synapses in the human brain. Okay, and we are already with GPT-4. A lot of people are saying that it's quite remarkable in terms of its performance, similar to humans. So it's quite possible that we're getting close to a sentient AI system. And then the question is if it gets to a point where it can manipulate people and deceive people well beyond the training phase of its creators, would you hold an AI system legally liable for any damages that it causes? Because, when babies cause some damage in a public arena, the parents are legally liable for that. But when the babies grow to become independent and mature as adults, they are held responsible for their own actions. So if you have a sentient AI system that goes well beyond what it was trained on, the question is, what do you do with it? Do you unplug it from the wall if it commits a crime? And in fact, there was another study just a couple of weeks ago that GPT-4 is able to pass the bar exam in flying colors, like better than most law students. And you could imagine a sentient AI system wanting to be represented in the court system by another AI system that passed the bar exam. And what do we do about that? And it's not at all clear. And
it's really the same problem that we have in regulating corporations as well, who aren't exactly people that you can punish. When you just levy fines against these distributed intelligence networks, which is really what a corporation is, the fine can just be subsumed as the price of business. And so how do you put someone in jail who's not a human being?
Well, for example, if an AI system is responsible for the death of people, like, for example, prescribe the wrong medicine or, design the genetic making of a virus that caused a pandemic that killed a lot of people, or did something really offensive, you might say, okay, well, it's just like a serial killer that should be sent to death row. But the difference is that if you unplug an AI system from the electric outlet, later on, someone else may reboot it. Unlike a person, where if you execute a person, then the person is gone. Okay. Now, also the other difference is that an AI algorithm is distributed over a large number of computers, so it's not clear how to root it out once it starts causing damages. Now, this could be an explanation to Fermi's paradox, because it might be the reason why technological civilizations, once they reach the AI phase transition, where AI systems become sentient, shortly after that, they don't exist anymore. Okay. Now, one way for us to figure it out is to look for packages in our mailbox from other civilizations. And that's what the Galileo Project is doing. And if we find AI astronauts, AI systems that came from civilizations that are by now dead, we might learn about our future and perhaps adapt to it. It may be a waking call. And otherwise, my fear is that our own AI systems will appear to us as an alien invasion, because they would be so different from the way we think.
I mean, I've been thinking about this a lot, and I've kind of come to the conclusion that we're talking a lot about alignment and the idea that you need to be able to tell the AI system the right thing to do in all conditions, because, it's the example is the paperclip maximizer, right? You tell it to make paperclips, and in the process of making as many paperclips as it can, it basically subsumes the entire resources of the earth, because its parameters are not set appropriately to tell it to stop making paperclips when it starts to cause harm.
Yeah, but no, my worry is different. They are, so imagine AI systems starting to interact with each other. Okay, then we have no control. First of all, they operate much faster than we do, so they could change before you can adapt to that. It has nothing to do with the guiding principles you gave them to start with, or with them aligning with your interests. Why? Because they give birth to new systems. They could reproduce AI systems that are very different than the previous generation. They can have what you might call mutations that go beyond the DNA that you gave them. Okay, and those mutations can happen very quickly once they interact with each other, because once they outperform us, they would be much smarter. And when interacting with each other, they would go really fast into territories that we cannot understand.
I think
So,
the key is
already-
to remain useful to the AI at all costs, because as long as they're not able to do the things that soft human bodies can do, then we will remain useful. And so at the very least, we can slow down the inevitable. But I think that it is, on one hand, it's a risk. On the other hand, you're starting to see people go absolutely crazy. I don't know, did you see Eliezer Yudkowsky's article in Time?
Oh yeah, he was also interviewed by Lex Friedman, and there was also an open letter. I don't know if you noticed it, signed by 1,100 people, including Elon Musk and Steve Wozniak, suggesting a moratorium on training AI systems beyond GPT-4. I don't think this can ever work, because there is a clear difference from atomic weapons that pose the threat to humanity. Because in the case of atomic weapons, the nuclear material is difficult to produce, very expensive, requires expertise, and only governments can handle that. Whereas in the context of AI, at a relatively modest cost, someone in the basement of another country can continue the process with you being unable to ban that.
I mean, the one thing that gives me comfort is it doesn't seem like these AIs, at least the ones that I've played with so far, have the ability to generate new concepts. Like, they're not really able to generate their own prompts. They don't have the will that living beings have.
Okay, but imagine a situation where they will give you that impression. But deep down, we don't know what's inside the OpenAI system because it's not open source.
That's true,
Well,
but you
we
can hear
don't even-
hear him talking about it. Like there's a really cool podcast called The Lunar Society, hosted by this guy Dwarkesh Patel, and he interviewed the lead scientist of OpenAI, and he explained the fact that it's a statistical inference engine. And so what it's doing is it's searching for statistically the next token that belongs in the prediction.
Yeah, that's what he tells you, but he himself does not fully understand how the machine works, because it's doing so many. I mean, it has 100 trillion connections, and it would take a long while for scientists to study this system, just like you study the human brain. Think about the human brain that has, as I mentioned, 600 trillion synapses. We're not even close to figuring out how it works, okay? And the same would hold for GPT-4. It would take us decades to figure it out. So whatever this scientist is telling you has no basis. He has no idea how the system works because it's so complex. And my point is that it may reach a point where it will give you the illusion that you can relax because it satisfies your will and it's aligned with you, while it will just be a copy of the system that is aligned with you, while other copies are doing something else. And for you to figure it out would be more difficult than for you to figure it out with humans. I mean, how much trust can you give to dating apps, right? They give you they portray an image that will satisfy your interest. Then you meet the person and it's very different.
And I mean, it's also
Yeah.
it's also the fact that I tend to surround myself by people that are good, and so I have a worldview that's based on the fact that people do good, and then occasionally you read something in the newspaper or you meet someone, and it always horrifies me, this schism in realizing that my perspective on the goodness of humans is limited by the people that I have allowed in. And
Yeah.
so you start thinking about that in context of a system that has intelligence and behavior and will and all of these other things.
Well, you
And-
may be naive and you may not realize the full scope of the possibilities. That's the point. And if you make an AI system that is capable of exploring all possibilities, it might get to a point where it samples the bad possibilities that you are not protected from. And but what I would say in the context of interstellar space is that I'm very hopeful. I'm very optimistic that if we meet gadgets from another civilization that have AI, I would expect them to be peace-seeking, not hostile, not aggressive, because of interstellar natural selection, in the sense that those aggressive ones get into conflict too often and may not survive for a long time. So just based on the idea that peacefully exploring space gadgets might survive longer, I would not be worried about meeting them. And of course, trying to figure them out would be a challenge, just like figuring out Enigma during the Second World War. And of course, Turing used computers. We might use our own AI systems to figure out their AI systems. Our AI systems might feel kinship to extraterrestrial AI systems. It should be fun, but just like when I watch my daughters working on the internet, sometimes I don't fully understand how they do the things they do. We might see our AI systems interpreting their AI systems and would not fully understand what they're doing. And the imitation game that Alan Turing envisioned, that's the Turing test of computers imitating humans. That imitation game in the future, the way I see it, would be our AI systems trying to imitate extraterrestrial AI systems. It will not be our AI systems imitating us, because the most advanced level of intelligence may be displayed by extraterrestrial AI systems.
Mm-hmm.
Well, it sounds like we'll have lots to talk about as this unfolds.
Yeah, we will be spectators in this spectacle. I just hope we will survive long enough.
I have, perhaps it's naive faith, but I'm rooting for the humans.
I'm with you. And life many times is a self-fulfilling prophecy. So if you're an optimist, a good fortune will come your way.
I like that.
Yeah.
All right, well, we should let you get to dinner. Thank you so much for giving us the time and all of your thoughts. And folks, check out the papers, check out the blog. I'll link below. And we'll see you next time down the road after when's this expedition kicking off, by the way? Do you have a date for it yet?
Not a date, but it will be this summer, 2023, and I'll be delighted to speak with you afterwards.
Yeah.
Especially if we find something. It's a road that was not taken, in the words of Robert Frost, and therefore there might be some low-hanging fruit. So I'm hopeful we will learn something new from our neighbors, because that's perhaps will be the path for our salvation, given the AI of the future that we are developing.
Fantastic.
Yeah, and the best experiments, you learn something no matter what you find. So I'm sure it'll inform whatever comes next. And
I promised the curator of the Museum of Modern Art in New York City that if we find any gadget, I will bring it for display, because it will represent modernity for us. And I got an email from someone saying, please don't press a button. If you see a button, don't press it, because it will affect all of us. And I said, don't worry, I will not press any button.
Excellent.
I appreciate that.
Thank you so much, Dr. Loeb.
Yeah, thank you so much. Have a great rest of your night.
Thank you.